Virga, and he's going to speak about ferrofluid monolayers. Thank you.
Thank you very much, Mark. And well, first of all, I wish to thank the organizers of the complex fluid program who have kindly invited me to join the program in the first place and to give this lecture today. So thank you, Daryl, and thank you, Len, for your kindness and your patience. Actually, this seminar has been scheduled and rescheduled a couple of times, so they've been really patient with me in rearranging this seminar. So I'll talk about ferrofluid monolayers, and before going into more details concerning the geometric arrangement of these fluids, I would simply recall what a ferrofluid is. Well, generally, ferrofluids are suspensions of magnetic nanoparticles with typical size ranging between 10 and 50 nanometers, carried by non-magnetic isotropic fluids. So these are suspensions which, of course, acquire some magnetic property, but these magnetic properties belong to the dissolved particles, and eventually they are transferred to the fluid as a whole. All right, I will just recall a few basic facts. First of all, just terminology and taxonomy. Ferrofluids are also called magnetic fluids or ferrocolloids. All these are synonyms in the trade. And to prevent coagulation, and in order to also make the magnetic interaction to play the major role in the system, often these colloids are coated with in such a way that dispersion forces can be essentially ignored. They are completely screened, so that, as I said, the only magnetic interaction plays a role in what follows. So at least this is the category of colloids, of nanocolloids, have in mind. Well, the major theoretical challenge that I will try to face in this talk is to predict and to determine under what circumstances such a system can really condense in a polar phase. This is, of course, as part of a long-going debate about polar fluids and the ways that polarity can really be transferred from the single constituent, which is a single colloid, to the phase. So whether or not the cooperative behavior of these particles can give rise to a polar phase. Of course, this is a huge challenge, and many people brighter than me have been defeated already. So I'll try at least to take advantage of what they have learned. All right, I'll apply a specific model, and the model I have in mind actually has been invented by Christian Holmwith in the audience, and there's a series of papers. And the idea he came up a couple of years ago was to imagine a pretty prolific variant of the usual dipolar colloidal sphere, and the idea comes from imagining that the dipole, which is still treated as a point dipole instead of living and sitting in the center of the sphere, is shifted along a radius, and it is radially oriented. And this extra degree of freedom, which is the distance between the point where the dipole sits and the origin and the center of the sphere, we'll see in a moment, will play a pretty important role, and actually it adds a huge phenomenology to these systems, which have been variously examined and inquired by Christian and his group, and as far as I understand, is still a source of inquiry. All right, before going any further, I already mentioned problems that people have already encountered in predicting dipolar phases, starting from these dipolar constituents. And in a classical language, I am in a very, a typical situation where Damocles had only one sword pending upon his head. I am even less lucky than he was, because two of them are actually hovering about my head, and one goes under the name of thermodynamic limit. I'll try to explain this, the content of this sword in a moment. And it goes like this. Dipolar interaction are long range. They decay in space like 1 over r to the third power. And we know that this is precisely the critical decay length below which there is no, including which there is no guarantee of the existence of any extensive thermodynamic quantity. It means that the free energy, for example, of the system is not just obtained by taking a density of free energy and multiply it by the volume, because the free energy and all other significant thermodynamic quantities can depend on the size of the domain occupied by the system. So it is non-extensive. And so the idea itself of predicting a phase by using the usual tools of extensive thermodynamics can be questioned in their root. So this is one pretty dangerous thought which is hovering about me. But there is another one, and the other is common in dipolar systems. It is well known, and Christian's simulations have shown, we'll come back to this later on, that particles which are endowed with these dipolar moments actually can form chains and clusters. And the idea that there are these, say, intermediate scale aggregates which involve a small number of particles is actually scary, because if you really have to imagine the formation of a phase, you need to decide whether the single particles with their single moment will take part in this collective behavior, or whether these intermediate players, which are chains and clusters, will be the players of your theory. So, and in general, you might fear that this lower scale organization of the particles in chains or clusters might even preempt the formation of a collective phase. In any way, you need to redefine what you mean. If you are really concerned about the formation of this intermediate aggregates, you need to redefine what you mean by the collective polar phase that might or might not arise. So I'm just mentioning these 2 points because these are the major concerns that will really undermine any continuum mean field theory that could be put in place to predict polar phase formation. Because as the title of my talk recites, I am mainly concerned with mean field. And actually, I'll try to express in this talk the interplay between this aggregation mechanism, or these aggregation mechanisms, and the possibility of forming polar phases as a result of a collective transition that could be predicted in terms of a mean field theory. All right, so let us go into the heart of the problem, and the idea is that we consider a two-dimensional system of monolayer in which all these particles are bound to glide on a given plane. So this is a plane upon which the centers, the C1 and C2 and Cn, of course, of these particles are bound to glide. But you see these are the point dipoles which point outwards, and you see that the point dipoles are away from the center. This is sometimes called a quasi-2D system. because it is surely two-dimensional, because the points, the centers of the spheres live on a plane, which is a two-dimensional manifold, but the orientation of the dipoles can be all over the place. So it is 3D if you think about the orientation of the moments, but it is 2D if you think about the place where.
So, going back to your remarks about the critical dimensionality,
Right.
Critical
Right.
decay length, that was presumably in 3 dimensions, and now you're in 2 dimensions.
Yes.
Oh.
Yes, correct. So the first sword is gone. Thank you.
Yeah.
But the second is still there. Yeah, this is one way just to go away from the thermodynamic limit. So now I am assured that due to this imbalance between the critical dimension and the dimension of space, now I'm allowed to take averages and to treat all these relevant thermodynamic quantities as if they exist, because they do exist. But of course, the real problem is concerning aggregation, and will be the leitmotif of this talk. It will come back and forth many times, and I hope to be able to resolve in some way this question at the end of my lecture. So I wish just to say a little bit more about the system, and just to fix the terminology. R is going to be the particle's radius, A is the shift, and it is always less than the radius. C1 and C2 are the particle centers. P1 and P2 are the dipole locations, the points in the spheres, within the spheres where the dipoles are located. M1 and M2 are going to be the dipoles moments. And this is, of course, in SI units, the interaction Hamiltonian. And R, as you see, little r is the dipole distance. So in this case, with the distance between the points P2 and P1, which of course is different from the distance between C1 and C2. And this, of course, will bring some complication into the picture. Rho, instead of r, is the distance between the two centers. Of course, r and rho are related, as will be shown in a moment. And little m is a dipole moment associated to each sphere. So E1 and E2 are simply unit vectors which designate the spin moments of the two dipoles. So M1 and M2 are the dipole moments, and we assume that they have both the same strength, which is little m. All right, just to a little more notation, EI is the individual spin, as I said. E sub r is the unit vector of the vector joining P1 to P2. E rho is the unit vector of the vector joining C1 to C2. Alpha is this dimensionless shift. It is a parameter which ranges between 0 and 1. 0 means that there is no shift, and so dipoles are sitting in the center. Of course, the limiting case is alpha equals 1, when the dipole actually sits on the periphery of the sphere. All right, these are evidences from Christian simulations, and you see that there is a change in behavior when alpha grows at this density, and for this specific system, you see that chaining occurs for small values of alpha, but if alpha exceeds the critical value, instead of a chaining, you get clustering. So this is, in a way, bad news, because at least in this experiment, you see that there is no way out. Either chaining or clustering would impede the formation of organized polar phases. All right, but we are not scared by this, we are not deterred by this, and we keep on going. And we just set up a theory, a mean field theory, that would describe the organization of these particles. Of course, it remains to be seen, and I hope to be able to show this a delicate and intricate balance at the end of my talk. It remains to be seen whether we can, within this theory, predict the aggregation, and whether there are means to, if we are able to predict when aggregation takes place, whether there are means to prevent the aggregation from taking place so that the theory remains justified. So this is a kind of provisional theory. We start by assuming that we are allowed to build up a mean field theory, and it remains to be seen at the end of the day whether at the end of the lecture, whether I waste your time and mine, or whether something can be done of this theory. All right, the idea is then to construct an average Hamiltonian, and the average Hamiltonian starts from the Hamiltonian that I have described, which is a exchange energy between the two spins, and essentially you imagine that particles are isotropically distributed around each other in the monolayer, and this of course is valid, such an assumption is valid in the absence of any aggregation phenomenon. I needed to stress this once more. And this is the expression that you get by taking this average under the assumption that the dipoles are uniformly distributed in space. So isotropically and uniformly distributed in space, so this sigma which arises out of this average is the surface number density. Big A here is area major, and this integral has to be taken in the exterior of the excluded region.
Why not the math function? Why don't you average the Mayer function rather than the direct macroscopic Hamiltonian of 1 minus e to the power Hamiltonian over t?
Well, I'll come back to the Mayer function. It will play a role in the aggregation later on, but at the moment it's just a choice. We simply replace the Hamiltonian. It is the usual. It is one of the possible avenues that you follow in constructing mean field theory. You simply replace the Hamiltonian, which is a spatial dependent, with the Hamiltonian, which only depends on the orientational degrees of freedom, and you take an average. You might disagree, yes?
Could I also ask?
If this diverges, saying
no, this doesn't diverge.
Volume is also tricky.
That's not theory of expansion.
But you have to average over the statistical ensemble, not over the. Basically, this would not depend even on temperature. So why would?
This does not depend on temperature. That's true. The temperature will enter later on. It is not the Virga expansion. The Virga expansion will come later into the picture. I don't see the problem, but if you see, we can discuss.
The problem.
Go ahead. All right. So this this area fraction f, which is a parameter which is usually considered instead of the surface number density, sigma is clearly related by geometric considerations to sigma via this relationship. And in the following, we will use in either f or sigma, depending on what we want to stress. All right, I just maybe a small remark concerning this region. Of course, the two spheres cannot penetrate one into the other, and so this integral has to be taken in the region outside the excluded. So this is the excluded region, so it must be taken the integral over the region on which the two spheres do not penetrate into one another. All right, well, this is just a remark that says that this quantity is indeed computable. It is a bit cumbersome, but it is a complicated integral, but can be performed and can be performed analytically. This U0 is a kind of a scaling energy which is defined in this fashion, and eventually you can reduce everything to an integral over the unit circle, and S is the arc length along the unit circle. And this V function, as you see, depends on both alpha and the orientation of the two dipoles. Of course, a clear-cut case is the one that arises when alpha is equal to 0, because in that case, then this becomes simply psi, and the expression for the average Hamiltonian simplifies a great deal. And it simplifies in such a way that the average Hamiltonian in this case becomes a bilinear form in the two spins E1 and E2. Generally, unfortunately, though it is computable, it is not a bilinear form in the two spins. All right, there are two interesting configurations that I would just mention, and the first arises just at this stage. It is the antiparallel configuration, in which the two spins are opposite to one another and parallel to the normal to the layer. So this is a situation in which the two spins are opposite to one another and oriented orthogonally to the layer. And this is indeed the configuration in which this dipolar Hamiltonian, which is obtained in the limit alpha equal to 0, is minimized. There is a reduction theorem that can be proved regarding the general average Hamiltonian that I have computed in the general case for alpha different from 0. And the reduction theorem says that all the critical points of this Hamiltonian actually occur when the two spins, E1 and E2, are in one and the same plane. So, though in general this would depend on 4 scalar parameters, 2 for each of the spins, the critical manifold is characterized only by 2 parameters. So we know that the critical points of the Hamiltonian must be represented in this way. So there is a single plane, which I call EXEZ, containing the normal, such that at equilibrium, when at equilibrium, it means at 0 temperature equilibrium, the ground state of the Hamiltonian are achieved in this case. All right, so this would be a way then to reduce the Hamiltonian if you want to explore the manifold of the ground state. You know that this manifold is actually described by only 2 parameters, and this is, of course, a great advantage instead of exploring the 4-dimensional manifold. And you can give an explicit representation, analytically explicit representation for the reduced Hamiltonian, which is the Hamiltonian reduced to the critical manifold, which is here just. And this is maybe is a little bit more telling, would be the energy landscape on the critical manifold. Of course, it is easy to see that this landscape enjoys a 4-fold symmetry, and actually this would be the minimum in this case for alpha sufficiently small. We see that we can prove that the minimizer, which is a ground state, is this point, which is a point with coordinate pi 0, which means that one dipole is along the normal and the other dipole is opposite to the normal. So this is the antiparallel configuration. So again, and we knew in a way this was to be expected, because for alpha equal to 0, which is a purely dipolar case, we knew already that this is a ground state of the energy. But this is a situation which persists for a certain interval, for a certain range of alpha, if up to 0.65 indeed, this is still the configuration with the least energy. And then there is a critical value of alpha, which we'll see in a moment can be determined analytically, at which indeed there is this switch and of ground state. Instead of being the energy minimized in the antiparallel configuration, it is minimized in the parallel configuration, but with both spins oriented on the plane of a layer. So this is a case where both angles are pi over 2, so the 2 dipoles are now parallel but orthogonal to the layer normal. And this is actually a situation that can be characterized, and this is just a pictorial way to describe this migration of the ground state, and this is precisely what happens. There is this critical value of alpha, which is alpha star, which can be, as I said, computed analytically, at which the minimum actually starts migrating from the anti-parallel configuration in the direction of the layer normal towards the configuration in which the two dipoles are parallel to each other, but they are on the plane of the layer. Of course, there is a problem, and the only theory I am familiar with, which is able to build a mean field treatment starting from this average Hamiltonian, presumes the Hamiltonian itself to be a bilinear form. And so the problem is, can we apply a general mean field treatment to an Hamiltonian like this, which is not in the form of a bilinear form? Well, the idea is to as the usual approach to mean field, which of course maybe in this audience need not to be explained in great details. The idea is just to replace the distribution function with a single particle distribution function, which we call rho. And so this is going to be the single particle mean field free energy. And of course, these averages are to be computed relative to the single particle distribution function. So this is our single particle distribution function. T is the absolute temperature, Kb is the usual Boltzmann constant, and these are ensemble averages. Of course, this works under the assumption that H is a bilinear form, which unfortunately is not the case in our situation. So what do we do? Well, this is possible to apply a theory which relies on a bilinear structure of the Hamiltonian only in the dipolar limit, which is the limit in which alpha is equal to 0. But since we want to appreciate and understand the presumably complex and rich behavior that arises for larger values of alpha, we needed to come up with some idea. And the idea is that we simply interpolate our analytically available Hamiltonian with an Hamiltonian which has this bilinear structure, which is precisely the same structure that applies in the limit as alpha equals 0, but the statement is that we construct what we call this interpolating dipolar approximation to our energy in such a way that the critical values, namely the ground states of the original Hamiltonian, are preserved. So then if you make this postulation, there is only one answer to this question, and you can determine these interpolating coefficients A and B in terms of alpha. Actually, A turns out to be independent of alpha, and B is actually expressed in terms of alpha only. And these would be the landscapes of the interpolants of the interpolating dipolar approximation. And again, by construction, well, these shapes are very similar and very close, even in quantitative terms, to the landscapes that we had already obtained exactly. And of course, what is encouraging is the fact that by definition the ground states of this interpolant are precisely those of the original function. And again, there is the same transition, the same migration that takes place between the two ground states. All right, so now we are in a position to apply traditional mean field theory. So we define this mean field, which is nothing but the average of the spin, and of course in the one particle distribution function, and of course the self-consistency equation is associated, the traditional one is associated to this mean field, and of course, in this case, the mean field is a vector, which is not necessarily, of course, a unit vector. Z is the partition function, and this C vector, C tensor, which is going to play a relevant role in our analysis, is actually a tensor which has this explicit structure. Ez is again the unit normal to the layer, and gamma is this transcendental function of, this rational function of alpha. Well, this beta parameter is something a little bit more complicated than the usual Boltzmann factor, and for reasons that I hope will become clearer in a moment, I call this the dressed interaction parameter. In a way, it weights the interaction magnetic energy against the thermal energy, but what makes it dressed in this formalism is the fact that it also depends on the density, on the surface particle density. And bar here is the coordination parameter. Well, strictly speaking, our mean field theory is the lattice mean field theory, and so it, in one way or another, requires the intervention of this parameter, which essentially tells us how many particles are interacting with a single probing particle in the mean field. We'll come back to this beta parameter, which is one way of measuring the strength of the magnetic interaction versus the thermal energy, but weighted against the surface number density. All right, the luck here is that we can give actually an analytic solution to the self-consistency equation, and actually the solution, analytic solution, says that the U's that matter are those which are eigenvectors with eigenvalue 1 of this tensor C. And of course, U equal to 0 is always a solution to this equation, which means that the non-polar, the apolar phase is always, or the isotropic phase is always a solution. And then you take advantage of the structure of this tensor C, and you realize immediately that there is only one vector. Actually, there are infinitely many vectors on the plane of the layer with eigenvalue 1. So you immediately know that your polarization, if any, will be certainly in the plane of the monolayer. And then this parameter here is simply the solution to the Langevin equation. And this L is a typical Langevin, traditional Langevin function, and so you need to solve this problem, which can also be visualized graphically. And you see, by simply plotting L of beta U against U, you immediately realize, and knowing that the Langevin function has slope 1/3 at the origin, you immediately realize that the critical value of beta, for which there are more than one solution, is beta equals 3. And this would be, of course, the configuration, the subcritical case. This would be the supercritical case with 3 solutions, 2 of them symmetric relative to the origin, and this, of course, beta equals 3 is a transition. All right, this is a bifurcation diagram, and up to beta equals 3, there is only the isotropic solution. U is identically 0. Then at beta equals 3, this solution becomes unstable, and a new stable solution arises out of the isotropic phase. And of course, just for to spare space, there is of course the symmetric branch of this graph, saying that we don't know precisely in which direction in the plane the polarization will arise. So this model simply predicts that there is a polarization that arises at this critical value of beta, which depends also, as I pointed out, on the density of surface density of particles exceeding this, when beta exceeds this critical value, then this theory predicts the polar phase. And this is the same condition made a little bit more explicit. Now, question is, what happens in the presence of an external magnetic field? Does the theory predict any kind of ferromagnetic or paramagnetic behavior? And can we describe such a behavior again in terms of an analytic solution? Well, the answer is yes. In this case, we introduce the average magnetization, which is simply defined in this way. And we introduce this dimensionless magnetic strength, which simply measures the strength of the applied magnetic field relative to the magnetic moment. And I simply, for later comparison, I will just remind you that for a paramagnetic gas, Langevin introduced this parameter, which is sometimes called the Langevin parameter, which is, as you see, is another way of expressing the strength of the applied field, but relative to the thermal energy instead of expressing it relative to the permanent moment carried by each particle. The interesting point is that these two-dimensionless parameters, alpha, h, and eta, are related via this dressed interaction parameter beta, and this will play a role in a minute. All right, the analysis here is a little bit more complicated, but again, you can express in a closed analytic form the solution to the self-consistency equations, and again, this is the algebraic equation to be solved. And of course, I make a long story short, and this is the conclusion of this analysis, which, as I said, is a closed form analysis, because all these solutions actually are known in closed form. So what happens is that if theta is the angle that the magnetic field makes with a layer normal, when the field is in plane, then you see that the bifurcation diagram gets perturbed. The two branches, which were perfectly symmetric, actually become unsymmetric, and this is sometimes called an imperfect bifurcation. The two stable branches actually reduce into a single one, which is the branch which is a globally stable configuration, and one of the other two branches actually preserves a certain degree of stability, but it is only locally stable, and this U2, which is a third solution, becomes, which is what is inherited from the straight line of representing in the previous analysis the isotropic state becomes unstable. So in this case, clearly there is a single branch which represents this growing magnetization. Of course, as the beta is increased, the degree of magnetization increases, and of course it is in the direction of the applied field. There would be a kind of magnetization in the opposite direction, but this is, first of all, less intense, and in the second place, it is unstable. It is enough to perturb a little bit the magnetization in the opposite direction to make it disappear. All right, then we can plot the magnetization as a function of the Langevin, and this is something actually I learned from Christian, that is really appropriate to compare and confront the magnetization predicted by this theory against the magnetization of the paramagnetic case, which is represented here by the Langevin line in the Langevin parameter. You see what happens here as a result of this is in the in-plane case, as a result of the cooperative interaction between the particles. you get an enhancement in the magnetization. And you get from here, these are two lines, one for beta equals 1, the other for beta equals 2, and the larger is beta, the larger is a departure from the Langevin paramagnetic case. So this means that in this case, there is this, and indeed, we know that the two dipoles in the interacting spheres are aligned to one another, and they lie on the plane of the monolayer. So in a way, the global response to the applied field is comparatively larger than the one that would be expressed by the same system, but in the gas limit, where there is no such cooperation between the dipoles. All right, what happens when the field is applied orthogonal to the layer? This is somehow less expected, because what happens is the following. If eta, which is this dimensionless parameter which expresses the strength of the applied field relative to the dipolar moment, if it is not large enough, and now what is large enough is dictated by alpha, because this shift alpha is hidden in gamma. Well, this is what happens. If beta is sufficiently small, then you see there is a response in the direction of the applied field, which is, of course, orthogonal to the layer. But if beta is sufficiently large, if the interaction is sufficiently large, this branch becomes unstable, and there is a magnetization in the plane of the layer that arises from this curve. So it means that this bifurcation line, actually bifurcation diagram, is in a plane parallel to the UZ equals 0. So it means that the magnetization in the direction of the layer is frozen along this path, and the magnetization in the plane of the layer grows along with beta. So the larger is this interaction parameter, the larger is the total magnetization, but the component of the magnetization in the direction of the field, which is normal to the layer, stays constant. What happens now if we make the same comparison? Well, if we make the same comparison, things change, because we get both curves. You see, all curves actually for beta equals 1, all curves are in between these two, one for alpha equals 0, the other for alpha equals 1. But all of them, as you can see, are below the Langevin curve, which means that in this case, the ground state is a state in which the two dipoles are antiparallel and in the direction normal to the layer. So when we apply a field in that direction, the system becomes less cooperative than it would be if it were purely a paramagnetic gas. So this makes sense. But this is interesting, because you have a system which is a ferromagnetic system which has a response to the field which is less than if it were paramagnetic. And this expresses the same point. Again, as beta increases, as this interaction parameter gets larger, the two curves which bound the behavior of the magnetization become farther away from the Langevin curve. So, all right, this might be nice or might be boring. Well, it depends on perspectives. But can we make any quantitative sense out of what we have presented so far? So is there any quantitative way to measure the degree of aggregation between these particles that would tell us whether or not such a cooperative mean field theory, which predicts a polar phase and which also predicts a specific response to an external field, which is of a different nature and a different kind, depending on whether the field is in the plane or in the direction orthogonal to the plane, does all this make sense and when? All right, to answer this question, which was, the motivation of this study, this talk at least, we introduce what is sometimes called the aggregation parameter. It is defined in this way. It is the number density for a dipolar system times what the absolute value of what we call the long-range second virial coefficient. Well, what is a long-range virial coefficient is simply the component of the second virial coefficient which does not depend on the hard sphere short-range interaction. So the idea is that you can always split the second virial coefficient into the sum of two quantities, one which is easily, for spheres, easily computed, and it is just the excluded volume plus something else which has to do with the long-range interaction between the dipoles. All right, and then you use this criterion, which was put forward by Misha, Paolo, and Margherita. They essentially proposed, long ago, that chaining and clustering in this in a system, like in a dipolar system, should really be not able to hamper the mean field cooperative behavior if this number is less than 1. If this number is greater than 1, then the opposite happens, and you should be very careful, and you should end believing in the meaning of any of these mean field theories. Actually, what I have said so far, if B2 were greater, even much greater than 1, would be completely senseless. So the question is, can we compute B2? That's a question. And this is not an easy question in general, because we need an accurate, precise, analytic computation of B2. And this, of course, for spheres, it's easy to compute the short-range component, but the long-range component for dipolar interactions has been long debated in the literature. So the problem would be solved if we were able to find a solution to an estimate as accurate as possible for this long-range virial coefficient, second virial coefficient. Well, this is the formal definition, and here are Meyer's functions that Ibrahim likes so much. So this is the definition of the second virial coefficient, and especially of the uneasy part, which, as I said, is the long-range one. Well, the idea is simple. This is presented in a more mathematic fashion, but it is the same definition which I have used all over again. V is a volume measure. B is a sampling volume, the sampling region. I assume that the system is distributed over the available space, and this E is available space, and I take this, I take out, as I did in my previous considerations, this ball of sphere, this ball of radius 2r. Of course, this is so easy because we are dealing with spheres. In general, this would be the excluded body between the two particles, and the excluded body is not always as easy as this. And again, these are R1 and R2 are the position vectors of the two interacting particles, and E is in this notation is the unit vector of the intermolecular vector. All right, if we plug in our H, this is what we get for the exponent of the exponential, and a new parameter actually comes in, and it is just the same as beta, but of course it does not contain the surface number density, because this is a different average. And we call this the Baire interaction parameter. It is related to the dressed interaction parameter via this relationship. And you see the relationship which links the two parameters, of course, depends on the coordination number, but also depends on this dimensionless number density. This dimensionless number density for the problem at hand is simply the number density multiplied by the cube of the radius. Of course, this quantity is subject to this constraint. It must be 4f over pi, and f is area the area fraction, so this quantity must be less than 4 over pi. Now, the cold fact here is that these three parameters, beta, lambda, and rho star, are not independent from one another. They are related via these three relationships. And we learned from the previous discussion that the interesting collective behavior which leads to a polar phase actually arises for beta larger than 3, for given values of beta that we are able to estimate. This cooperative behavior arises. So the idea here is the following. We treat lambda as a free parameter, and then we imagine a target value of beta for which some interesting behavior takes place, and once this is done, then we express rho star via this relationship, beta over pi eta bar or times lambda, and we make sure that this is less than 4 over pi. So this is the idea, and this is a strategy that we are going to apply in the last minutes of my talk. We imagine a target value of beta for which there is an interesting behavior, and we treat rho star as a function of beta and lambda. Actually, we treat it as a function of lambda, and keep in mind that it makes sense only if rho star is less than 4 over pi. All right. The piece of luck here is that indeed it is possible to compute analytically the long-range dipolar second virial coefficient. And it is given by this expression. This is a closed form expression. And as you see, it is d cubed. D is the diameter of the sphere times this integral, which depends only on lambda. Gamma here is the incomplete gamma function, and gamma of A is simply the complete, or the gamma function where x is set equal to 0. And this epsilon here is indeed a function of theta. So this is the exact expression for the long-range dipolar second coefficient, virial second coefficient. And this is a graph from 0 to 10 of this function. And actually, this dashed line is pretty interesting because it is a Jensen approximant. It so happens that this function in the integrand actually is a convex function of lambda. And being a convex function of lambda via Jensen's inequality, you can actually estimate this behavior, which is again explicit, and as you can see, could be a very good approximant for lambda up to 4. But as I said, the main point here is that we do not need any approximant because we are lucky enough in this case to have the exact formula. And now we just play our final game, and we put all pieces of information together. We take advantage of the fact that we know exactly what the second virial coefficient for the dipolar interaction is in this case, and we play this game. So this is my last transparency. So just bear with me for 2 minutes. I'll try to convey the way such a transparency should be used in order to test the theory. All right. There are 3 pairs of curves, and with this color code, beta equals 3 is the blue code, the green code is 6, and 9 is the red code, which means that these 3 curves, these 3 pairs of curves, are actually drawn for 3 different objective values, target values for beta. And I started from 3 because we know that above 3, all the interesting behaviors predicted by the theory take place. Now, the solid line represents the aggregation parameter, which, as I said, for a given beta is a function of lambda, which is given here. So what you need to do, you need to stay below 1. At the same time, you need to be careful because the dashed line here represents the dimensionless density rho star, and this rho star must be below 4 over pi. So the theory makes sense and can be applied if two things happen, that the V2 is less than 1, if the aggregation parameter is less than 1, and if the corresponding density, dimensionless density, is less than 4 over pi. So for example, you pick up lambda, and lambda is 3. You pick up lambda 3 in this case. You go up to this point, which is the intersect with the beta equals 3 case, and then, all right, you say, I'm lucky enough, I am below 1. But at the same time, I needed to pick up this density in order to make the theory applicable. So it means that, as you see, there is ample room here, there is plenty of room here to obey the aggregation criterion. But one has to be very careful in relating the number density appropriately to the value of lambda. So if you take a random value of lambda, you are bound to be away from this legitimate strip. But if you choose lambda appropriately, and more importantly, you choose the corresponding number density in the way which is tuned by this curve, then you can apply the mean field theory, and it means that according to this criterion, there should not be any chaining or clustering that would prevent you from applying the mean field theory and from believing in the predictions of a collective polar phase that such a theory make. All right, this is my really last transparency. This is a joint work with Chuck Gartland and Marco Piastra from my university, and I really profited a lot during my stay here from a number of discussions with Christian Holm and Misha Osipov, and it is not, there's no exaggeration to say that without their input, I wouldn't be able to put this together. And of course, I take responsibility, full responsibility for all my misunderstandings. Well, thank you very much.
Questions?
This is a sort of variant on a 2dxy model, and 2dxy models are known to have rather peculiar low temperature behavior. And on the other hand, you've got a long range potential. If you had a 2D XY model with a long enough range potential, then a mean field treatment would indeed work out, and you might be able to get a low temperature ordered phase as opposed to a low temperature effective kind of phase. So do you think that the fluctuation type problems, the sort of famous Kostelik-Stowers low temperature problems for a system with this kind of symmetry are likely to be a problem? Or do you think that fortuitously your long range potential, which was threatening to give trouble in the 3 dimensions, which caused you to restrict yourself to 2 dimensions, you think it might just rescue you?
This is my hope, but I mean, more than a thought, it's a hope. So I was, and I'm still aware of the pitfalls hidden in such an approach. And I found refuge in this quantitative estimate of the aggregation parameter, which I think is something that could be useful also in your problems concerning these nanoparticles in liquid crystals, though in that case, of course, for pseudocylinders, which would be the shape more appropriate in your case, I wouldn't know how to estimate analytically the aggregation parameter. I mean, estimates for aggregation parameters have been known for a century in dipolar interactions, but these are either valid in the limit of very small lambda or valid in the limit of very large lambda. The large value, the large limit, the large lambda limit was computed for, I think, by degli and Pincus for the first time. And of course, having all these asymptotic estimates, you are not able to answer these questions. I mean, now I think we have a tool, since we were able to give an analytic exact formula for the aggregation parameter, which is nothing but the second Wheeler coefficient, valid for all values of lambda. Now, this criterion at least can be tested. But we have simulations as well. So the idea is, now that we know how to tune the system, we might just run simulations and see what is the role of fluctuations in this case. This is my answer.
More questions?
This is a bit of a deviation from what you were talking about, but there's a lot of interest in non-classical mechanisms for crystal growth, which involve the aggregation of charged mineral nanoparticles, and there are some theoretical predictions that suggest that the way those approach one another is largely governed by long-range dipolar forces between these ionic little nanocrystals. Now, of course, there are two things that are different there. It's in 3 dimensions, and of course, normally you'd expect there's some kind of screening going on, so it's more like a Yukawa kind of potential. I mean, do you think it would be possible to apply the same kind of ideas to determine an aggregation criterion?
Yeah. Well, yes, my answer is a tentative yes. I'm not aware of this field of research, but this treatment that here was successful for the 2D aggregation parameter actually, I had no time to report on that, actually was successful as well in 3D. So we have a formula for the 3D aggregation parameter for dipolar interactions. And I mean, this is the only thing I can say at the moment. Presumably, by applying that explicit formula to this case, one might learn something. At least one has a number. I mean, so far, when I've given talks like this, I was, as many others were, hand-waving. So I say, well, look, if the system is sufficiently dilute, then you can hope that a kind of mean field treatment can be successful. But now, the major point here is that this aggregation parameter is not just the density, which is there, but it is also a pretty nasty function of the interaction parameter. And there is no guarantee that if you take the density sufficiently low, you can make this B2 sufficiently smaller than 1. So I think that this is really the quantity to compute and to test against experiments and simulation.
Thank you.